Welcome to CS 320, Chapter 7, where we're going to discuss Kleene's theorem. Now we're going to spend quite a bit of time on this theorem, so let's first look at what this theorem says. Now, the first question we have these three methods of declaring or defining a language. So we could define it with a regular expression, with a finite automata, or with a transition graph. Now the question is, which one of these three methods is the most powerful. Now, not the easiest to use or the easiest to understand, but the one that can define the most number of languages. Now, we might think that transition graphs are more powerful than finite automatas. Remember, we relaxed the rules of finite automatas to make it easier to use, and it has that one property called non-determinism. Now, transition graphs have this non-deterministic property in that you can just magically choose the right path and land at the final state. So it's kind of, even though if you're to do it yourself, you kind of have to guess the right state, but because you can keep guessing until you find one that works, really it's like a magical transition that somehow knows exactly the path that you should follow. Now you would think that would give us more power to be able to define more languages, but that's not the case. These three languages are actually, or these three ways of defining languages are actually equally as powerful. So what Kleene's theorem says, if we could define a language with a finite automata, we could define that same language using a regular expression or a transition graph. Same thing, if we could define a language with a transition graph, then we could also define it using a regular expression or a finite automata. So these three methods of defining languages are essentially equal. So now we have to prove that. So the proof of that is going to be done in three parts. And we're going to do parts 1 and 2 today, and then we're going to do part 3 in the next few lectures. Now the proof of this theorem is, again, three parts. Part 1 is that all finite automatas can be made into transition graphs. So this is a proof by construction. What we're going to do is we can prove that if you give me a finite automata, I can generate a transition graph that will accept the same language, or construct a transition graph that accepts the same language. Then in part 2, we're going to take any transition graph and come up with a way to construct a regular expression that accepts that same language. And in part 3, we're going to take any regular expression and figure out a way to construct a finite automata that accepts that same language. So let's do part 1. And you know what? Part 1 is actually already done. Just by definition, all finite automata are also transition graphs. Now, transition graphs include extra things like multiple start states, null transitions, non-determinism, but they also include finite automata. So by definition, all finite automata are transition graphs. So now we're done with part 1. Now let's go, we're going to create a proof by construction that we could take any transition graph and generate a regular expression that accepts the same language. And then in later lectures, we're going to cover part 3 that says we could take a regular expression and construct a finite automata that accepts that same language. Now, once we've proven all of these parts, we have proven Kleene's theorem that says finite automatas, transition graphs, and regular expressions can all express or be used to define the same group of languages. So if we could define a language using any one of these three methods, we can also define it using any other one. And it works because if we define it using a regular expression, we can convert it to a finite automata. A finite automata is a transition graph. If we could define it with a transition graph, then we can generate a regular expression that accepts the same thing. And if we want to, we can take a regular expression, that regular expression, and turn it into a finite automata. So because we have this cycle here, we could take a finite automata to a transition graph to a regular expression to a finite automata to a transition graph. No matter what we use to define a language, we can always convert it and use one of the other two ways to define that language as well. Okay, now to prove that all transition graphs can be converted into a regular expression. Here we have a transition graph. It has two start states and two final states. Okay, now you can read through the proof and all the steps. I'm just going to show you an example of how to do it, but make sure you refer to the textbook. So in step 1, we need a single final state. So we're going to add a new state here. We can't have two final states. So we're going to add a new state, and we're going to take our current final states and add what's called a null transition to our new final state. And as we do that, we're going to erase these as final states. So now they're just regular states. Okay. Now sometimes you have transition graphs that already have just one final state. Now the one thing that you have to look at with your final state is it cannot have edges leaving the final state. So if it does, you need to add in this new final state. So for example, if this had an edge going out to there, or even a loop going out to there, you would need to add a new final state with a null transition that didn't have any edges leaving. We need to do that, the same thing for the start states. We need a start state. So we need to do the same thing for start states. We need a single start state, and we're going to just do a null transition to the previous start states, and then of course erase the start state from our previous start states. Now same thing except for its opposite. We can't have any edges going into the start state like that. So all the edges connected to the start state have to be leaving. So even if we have a loop that's an edge coming into the start state, we would need to create another start state with a null transition going into that if it had any edges coming in. So if you start with a transition graph that has just a single start state, that start state can't have edges coming into it. If it does, you need to create a new one. So that's step 1. Now the book does talk about step 2, saying combining parallel edges. So let's say that we had one edge that went this way and one edge that went that way. What it means to do is combine that into a single edge. And normally we could kind of put a comment there. So let's say there was an edge with an A. We could combine and put that A as a regular expression, so we could either get this or the A to move from this state to that state. But currently we don't have any parallel edges. We might create some as we move through these steps, but we'll keep going. And this next step is to eliminate states. So our goal is to eliminate each one of these blue states, or the original states. We keep the single start state and the single final state. We don't want to eliminate those, but we want to eliminate all the rest of the states without changing the language that this transition graph accepts. So if we eliminate a state, and I'll show you how we do that, then what we end up putting on that state is a regular, or on the edges is a regular expression. And eventually, when all of the states are eliminated, we'll have one big regular expression. So we'll have a start state, a regular expression, and we'll land at a final state. So let's go ahead and pick a state to eliminate first, and we'll go ahead and eliminate state 1. So if you notice, I could go from this state to state 1 and then into state 2. So that will be, this is actually pretty easy to eliminate. The way we eliminate it is we create a new edge that's like, okay, I started here, I go through here, and then I land in there. So I create a new edge. This was the start, that was the end. So I create a new edge, and then along that edge, I type or write out what I had to do to get there. So I had to go through a null transition and then to A and B. Now, a lot of people ask, well, that's null word. Can I just eliminate it? A lot of times you can, but sometimes you can't. It might change the language if you eliminate it. But it doesn't hurt to keep it in, so there's no reason to remove these when we're doing that. So I just recommend keeping it in just so that we don't have any problems in removing it when it actually might change the language. So then we can erase state 1 out of from our transition graph along with its edges, and we're left with that. All right, let's do something that is a little more complicated, okay? In fact, I'm going to do maybe the most complicated elimination that we can do, and that is eliminating this state right here, okay? This state has, now we're going to ignore the loops, but it has two edges coming into it, and then two edges leaving it, now ignoring the loop. So what that means is we're going to have to create four new edges, an edge from here to here, from here to here, then from here to here, and from here to there. So that's four new edges that we're going to have to create. Let's go ahead and draw them in. So this one, and this one is going to have to hop over there and go to there. And then finally, this one right here. Okay, there, I've drawn that a little bit better. So now we're going to have to come up with a regular expression for each one of these new edges coming in that's like following the path. So we start here, we go to state 2, we can take this loop as many times as we want, and we end up in state 4. So what's the regular expression that accepts that? Well, it's the null word A, B, which is like taking this edge. Then we got the A as many times as we want. So that's an A star. We could take it 0 times, we could take it 100 times. And then finally, we go take this edge to land in there. So that's a BA at the end. Okay. Now let's work on this edge right here. Okay, and that is taking this, doing the loop as many times as we want, and going through that way. So let's write that. It's a null AB, which matches this. Next, we're going to add the A star. And finally, we're going to add the B. Okay, next we have this edge right here. We can do this edge next. So that's 3 B's, A star, B. And finally, we have this edge right here, which is starting from this state, ending in that state. So that's 3 B's, A star, BA. All right, now that we're done with that, we can erase state 2 out from our transition graph. So, and any of the edges and labels that were connected with it. All right, next, let's go ahead and eliminate. We'll do state 3 next. So that's pretty easy. All we need to do is, notice there's two edges, or one edge coming into state 3 and 2 edges leaving. So what we need to do is add a new edge that goes from here to here, and a new edge from here to here, because we're eliminating state 3. And so to get from here to here, we go nullward plus this. And then to get from here to here, it's nullward plus this guy right here. And I'm going to cheat and just add the nullword onto that and then kind of modify this edge. So it's that edge. And now we can erase state 3 out of it. Now this does get a little messy, and it's really nice using kind of a whiteboard because you can erase really easily. If you're going to do this on paper and pencil, you might have to draw it down a few times. And what I've done is I've created, through that last elimination, I've created 2 parallel arcs right here. So to fix that, I'm just going to go or null B, 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 A star, B, A. And so that this part right here, we can either go from here to here or here to here. So now I did the or. We can either have this or that. So that's how I came up with that. And now we can erase this edge right here. Okay. So go ahead and erase state 5 next. And so all that's going to do is it's going to add a null onto the end of both of these. And we're going to redirect that to the final state and redirect this one to the final state. And now we can erase edge 5 or state 5 along with its edges. And now we have another parallel arc right here. So 2 parallel arcs. So I am just going to say or this A, B, A star null. And now we can erase this one. And finally, we have one more state to erase, and that's this guy right here. And that's going to be pretty easy. All we have to do is add a null onto him. And we'll erase this 4 and combine it that way. And now I'm going to put parentheses around this guy. And I'm just going to do a big or and put parentheses around this guy right here. And all I'm doing is combining these two with this big regular expression. And then we can erase this edge and this edge. And now we have, and just pretend like this or this is one big regular expression for just one edge to go to the start state to the final state. So the final regular expression that accepts the same language as that transition graph would be null A, B, A star. And just so you know, I'm just writing this expression down. B, A, or null B, 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 A star. Sorry, B, 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 not, got an extra B in there. A star, B, A, null, or null, and now I'm writing this part down. B, 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 A star, B, null, or A, B, A, sorry, I forgot the null in front of there. And so this is a regular expression that accepts the same language as that original transition graph. Now, there's probably no way that we can really make sense out of this. We're not saying that this is a better way to define the language. That transition graph was much easier. But by following these steps, and we can do these steps on any transition graph, we'll always generate a transition graph that looks like this with a single regular expression on it. And that this right here is that regular expression, and that regular expression will accept the same language. So that's the proof for part 2. So for your homework, you'll just practice eliminating states out of transition graphs and generating their regular expressions. Now, after watching through this video and editing it, I noticed that as I was writing this down, I wrote a B with this red pen that disappears, and the B disappeared out of it. So the correct answer would have a B inserted right there. So you do have to make sure you write down everything correctly. Now, another thing that I did is I had 2 parallel arcs up here, and there are also 2 parallel arcs down here, and I combined these two, but I didn't combine the 2 down here. And I ended up working out okay. You can either combine it beforehand, or I just eliminated it and ended up combining it later. So the order in which you eliminate the states will change the regular expression you get, but those regular expressions will be equivalent or define the same language. So if your buddy eliminated the states in a different order that you did, don't be surprised when you have a different regular expression. As long as you did the steps correctly, both of you would have a correct answer.